Okay, since a lot of people are upset, we're gonna go over what is actually posted, and it is not. These are not my words. Okay, what we're gonna go through is definitely what they're posting and what they're teaching or indoctrinating people to believe. And after we're done with this, you are all gonna realize that there's no point in putting any type of hope, belief, nor trust, okay, in anything regarding gravity. So let's just move on, and we're gonna move in there real fast. I'm not gonna sit here and bullshit. This is gonna be like really fast. Um, oh, there, see, as you guys can see up here, this is from Ohio State, and there's other already. I did already have some windows open that we're gonna go through as we go through this. Like I said, I don't want to spend a lot of time doing this. I just want to hurry up and destroy the gravity beliefs. Okay, so this is Space, Time, and Gravity, Astronomy 162, Introduction to Stellar, Galactic, and Extragalactic Astronomy, the key ideas, general relativity, modern theory of gravitation, matter tells space-time how to curve. Okay, and then curved space-time tells matter how to move. So then tests of general relativity, perihelion, precession of Mercury, bending starlight near the sun, the binary pulsar. These three are based on these key ideas, right? And we already seen that they're saying that matter tells space-time, and that curved space-time tells matter. Tells, tells. You guys tell me how space-time talks or tells or communicates with matter. How does matter communicate back with space-time? That's total crap right there. So right off the top, it's dead right there. The very beginning, it's over with. But we'll go on and we'll, maybe we'll see something that, maybe will give us a reason to maybe, believe it. If you see what you like, if you want to put trust in it, if you want to put hope. All right, let's move on. So, Newtonian gravity, matter tells gravitation how to exert a force. Again, this is not general relativity. This is the Newtonian. They're going back a bit. So, matter tells gravitate. Here we go again. All of it matter. Like, matter talks. Like, the only matter I see talking is like us humans. We talk. We tell each other things. That's communication. All right. So this whole thing about matter talking and space time talking is right off the top. There's nothing to back that up. It's just right off the top. That's just a really, really weird fucking insane claim. It's just there's nothing. It's totally a worthless statement. It doesn't mean a fucking thing. Okay. A force tells matter how to accelerate. Okay, so then we have these, the acceleration and we have the equations. So Einstein discontents. In other words, why Einstein didn't like the shit that Newton was saying. Einstein had two objections. He was against two things. First thing, the force law, line one, implies instantaneous knowledge of a distance, but information is only transmitted at the speed of light. Now, at the speed of light, what? Speed of light, okay. Now, the reason why he would say that is because he was using that concept himself about a speed of light. Okay, so this is going from one fairy tale about space time and matter talking to each other to now a speed of light. First of all, light comes in many frequencies. It's that simple. When you say speed of light, which type of light are you talking about? There's many, many different types of light. Shit, are you talking about LED? Are these LED lights? Incandescent light? Like what kind of light? Like there's light is that's a broad general like insane concept again. Speed of light. That doesn't even make sense. Furthermore, in his time and era, there was no way to actually grab light, and then even to this day, like, there's no way to clock the speed of light. It's not like California Highway Patrol is sitting on the side and a ray of light passes by, and the California Highway Patrol pulls out his speedometer and clocks the speed of light, going beyond the speed limit, and then he decides to try to catch up to said speed of light and pull it over. It doesn't work like that. That's just stupid. That's just really dumb. Okay. Number 2, the mass m appears in both force and acceleration lines, but disappears from the final acceleration. This seems to be coincidental. Well, it's not that it's coincidental. It's the word right off the top. The same mass m appears. So appears is something like a ghost. It appears. And then it goes on to say about it, in both the force and acceleration laws, but disappears. So if something appears and disappears, but it might be coincidental. Now, this is going to be even funnier. So I frame no hypothesis. Newton could not explain physically what gravity was. He considered that gravity is an action at a distance. Okay. He also said he had no hypothesis for what agent communicates the gravitational force across empty space. Right now, they're calling that the graviton, the mythical graviton, which coincidentally appears and disappears out of existence. This is too easy. Like we're not even like halfway, and it's already fallen apart. It's basically a fairy tale. So, the principle of equivalence, the first postulate of the special relativity, states the laws of physics are the same for all uniformly moving observers. That is a very, very, very big claim to make. You cannot claim what others are observing. I don't care what that's insane. That's like saying you know what a dog can see too, then, and a cat and all these other animals. You can't say that. We don't know how they see. They're like, oh yeah, they see in color. They don't see in color. We don't know. We could theorize and hypothesize because of how our eyes are compared to theirs when you cut them open and chop it up and look inside of it. Other than that, those are assumptions. That is laws of physics. Laws. that is a really big claim to make. That all observers see the same thing. That doesn't. Okay. In 1907, Einstein generalized this statement: the laws of physics are the same for any freely falling observer. That's like a way of just to like deflect what's going on. Like you just like, oh no, well it's the same, but only for the people that are falling. Like what the hell? What does that even mean? And we're like, oh man, this is gonna get funnier and funnier. So as of now, we're already seeing that space-time talks, matter talks, shit appears and disappears out of existence. And then sometimes things may look the same, but they're not looking the same, but sometimes they do. So general relativity, gravitation binds matter to matter. But how does matter know that the other matter is out there? I mean, this goes on, and I'm not gonna keep going on this because this is just it's ridiculous. We're gonna like fast forward a little bit. So Einstein showed that space and time are relative, not absolute. Only space-time is observer independent. Again, that is something really broad and bold to make. Only space-time is observer independent. First of all, we don't observe any space-time. Okay? We don't go outside and see their space-time. Hey, what's up, space-time? And space-time, we're like, hey, we walk up and space-time is talking to matter, and matter and space-time are talking with each other and having a conversation like, oh, excuse me. And you butt into their conversation. No, it doesn't work like that. There is no space-time. It's like only space-time is observer independent, but nobody's observed space-time independently. like that's just like this is straight insanity. And oh, keep going. Like we're gonna keep going, and then by the time we're done, you're gonna understand what the hell Einstein was saying. This is funny. This is gonna be funny. So, an object moves along the shortest path between 2 points in space-time. That would indicate or imply that space-time would have to be flat and two-dimensional, like on a piece of paper, because the shortest distance between 2 points is a straight line. That is a definite absolute right there. That is an absolute. Okay, so hold on. Let me take a drink of this. I'm drinking beer. I had a nice dinner, by the way. So the shortest path on a flat surface, as I just stated right now, and that's something that we learn in telecom. The shortest path between 2 points is a straight line, and parallel lines stay parallel always. On a curved surface, the shortest path is a curved line. That just doesn't make sense. Lines that stop parallel can converge or diverge at some distance away. That is not true. On a curved surface, lines seem to diverge at a distance away, or converge, I mean. That is not, they don't, parallel lines, I don't care if you put parallel lines on a curved surface or not, they do not touch each other. You only see that way. And ironically and coincidentally, when you're looking at a flat horizon, you also observe that same observation. Parallel lines look like they meet each other, whether on a flat or curved horizon. So in empty space, space-time is flat. Should I repeat that again? Let's repeat that one more time. In empty space, space-time is flat. Okay, so it's empty, right? It's empty. And space-time, something we've never seen, and we just keep imagining, is flat. Woo! Clap, clap, clap on that one. Okay? Moving objects follow straight lines. Yeah, blah, blah, blah. Just keep moving. That one was too funny. That one right there. Geometry of the unifier. Right now that I know you guys are probably like really pissed off. You Globies were like, I didn't even know that. You guys are mad. Like, you guys are learning. You know why? Because you guys recite a bunch of crap and you guys never actually sat to read and then try to comprehend and understand what you're reading. So I'm helping you guys, okay? We're going to go through this together. We're going to all get through this together. All right? We're all going to learn right here. All right? I'm going to learn how stupid you Globies are. And you Globies are going to start to learn. So you can learn to learn again. Your indoctrination is coming to an end right here. Curved space-time. Matter curves the space-time around it. That is another claim. Let's see some matter curving some space-time. We have never seen space-time. Who is space? What is this space-time? What does it look like? What what shape? What form? What is it? And how is matter curving it? Like what matter curves it? Does it grab it? You know, because from my understanding, you like it distorts it. Well, how does it distortion? If you look up the definition of distort, I mean like ripping it apart and twisting it. Like you tell me how matter is grabbing space time and twisting it. It doesn't make sense. That's just a really stupid, dumb, fucking claim. It doesn't make sense. Matter curves of space time around. That's as dumb as saying something in the Bible. And I'm not trying to talk bad about the Bible to everyone that excuse me, they may be religious right here. Okay, I know all about the Bible, by the way. I read it more than once. I read that Bible from front to back. Oh, I've read it more than a few times. Mainly because Newton told me to do so. Okay, so moving forward. The least pass are curved lines, more mass, greater space-time curvature, closer, greater space-time curvature. Again, space-time curvature. What is that? Where is it at? Where do we see it? When can we do a science experiment with it? I want a physical, actual physics experiment. So that means physical. I mean, we want to see it. We got to touch it. We want to be able to do something with it, manipulate it, test it in many different... And you guys are going to be like, yeah, we do. Not like, no, you're testing how shit falls. Like, is it falling faster than the other? Who's falling faster? No, but that's not the mechanism that we're trying to find out right here. All right? So we're trying to learn here. What is this thing? What is the mechanism behind falling? Why aren't you globies falling off a spinning globe? We're trying to figure this out together, guys. Okay? All right, let's move. So, Newton would have said, now look, I read a lot about Newton, but I could tell you what, I don't know what the hell he would have said. At any given point in time, he could have said some insane crap because he was totally fucking lunatic. Straight up lunatic. Lunacy. That means he spent a lot of time looking at the moon. Yeah, Luna. Luna means moon. Lunatic means looking at the moon. So it feels a force deflecting it from a straight line path. It feels a force deflect. It feels. What feels what? Like it feels. Like it feels. It like what is it feels like? God feels, the dog feels, the cat feels. They're like, no, space-time feels. So space-time feels now. So space-time talks, it communicates, and it feels now. This is definitely some type of divine God, like, because it's not really even a force. Okay? It feels a force. Okay? So, new theory of gravity, general relativity serving as matter tells space-time how to curve. Curved space-time tells matter how to move. How are they communicating? What is this? How are they talking to each other? What is this? Like they're telling each other things. How are they? Where? Where are they? Where's this communication at? Where's it going? Can we get the transcripts? Can we record this communication? Is it like a formal, like, what type of communication is it? Is it verbal? Is it sign language? What? So replaces the Newtonian idea as a force. There it goes. So replaces the Newtonian idea of a force with the curvature of space-time. It's a consequence, not a force. So it's no longer a force, it's a consequence. And yeah, it doesn't say right here the consequence part, but I could find that for you. So GR has withstood all experimental tests. Like what experimental tests? Like give me one real physical experimental test. And they can't. Here's what they'll do. Here's what we'll start doing the drawings and the lines, the dots, Newtonian. So here we go. They start fighting each other. Einstein beats Newton on this one. Newtonian gravity predicts these arc seconds of a century. And here's where they start going with like, first of all, a century is 100 years. 100 years is part of time. Time is already, we're known as, time is supposedly an illusion already. We already know that time is based on many different factors. The season, the dates, the holidays, the culture, the place, the location, all of that is time, and that's individual. You cannot say that someone, in closer to the North Pole during winter time will see the same type of climate as someone towards the Antarctic. They don't. So you can't sit there and this all is about a century and an arc second of a century and a little fraction of a century and no, it doesn't work like that. So in general relativity, space-time curvature changes as Mercury gets closer. This is all like really weird stuff. It gives the orbit a little twist. Ooh, a little twist. What does that mean? What does that mean? What do you mean it gives the orbit a little twist? That means the orbit is not flat? So supposedly space-time is flat. So how is this twisting a little bit? Bending of starlight. Blah, blah, blah. So as we can see, this was easy to pretty much dissect, and we will move over on to the next one, just to let you know that it was not just on one article. It is definitely across Google. We're now on Google. Space-time tells matter how to move. Anyone can look this up. And in 12 words, space-time, and it has to be 12. Ironically, 12. Space-time tells matter how to move. Matter tells space-time how to curve. That is the stupidest. That's not science. That's not. A ghost told a piece of material how to move. And then the piece of material told the ghost how to curve. On a flat universe. So here we go. We'll keep going down. As you can see, space-time tells matter. Space-time curvature is the controlling motion. How does it control it? There's nothing. How great is space-time geometry? So it just goes on and on. That space-time tells, and we have some of them where they start telling. They start questioning all that. Space-time doesn't tell matter anything. Locally, to the matter, all space-time is flat. Matter, solely under the influence of gravity, always moves along a straight line. Now, if matter was under the influence of maybe alcoholic beverages, or marijuana, or maybe under the influence of some hardcore narcotic, it wouldn't move along a straight line in a flat space. This is so stupid. This is so dumb. This is the dumbest shit. It's just dumb. It goes on. So let's go on to so not only is space-time flat, it's also expanding. Let's get some images of what it looks like when flat space-time is expanding. Ooh, nice. Look how so much of it is an expansion. So look, that's totally proof. We see space-time is expanding. Oh, I like this one. This got like a cube going on. Like, ooh, it's still dimensional. They put a cube in there. I made fun of this one so many times. This is so funny. Because this one is Big Bang. See that? And there's the other one. I've memed these. These are not my images. I put green letters over them and made fun of them. Because these are memes on their own. What do you mean space-time is telling? Like, how are these things telling? Yeah, space-time is talking with matter. Okay? But see that edge back there? See that edge? You see how the different forms of expansions? Let's click on that one. Oh, yeah. So many different types of expansion. We have the decelerating universe. which if gravity was that strong, everything would be crunching. It would have never even expanded. It would have stayed. It would have stayed a little nothingness dot of in the middle of nothingness, nowhere. Okay. Then you have the accelerating one. This one is the one that they're pushing on right now. So as it spreads out, dark energy. See this darkness? They're like dark energy is gonna rip it up, and then it starts ripping it up, and then it just becomes nothing supposedly. Globy's got edge. So here we see space-time. It's flat. This is what space-time must look like. Cause I see a lot of this. So space-time must be like a bunch of little cubes. And they look like kind of like soft spongy cubes. Cause you see, cause it curves. When you put matter on it, it's like the sponginess curves. But there's more over here. See, the sponginess curves. Oh, this was really weird. Like that is really weird. Like come on, man. I like this one. This one's funny because this was like boom, magical, and it just like that one right there. That one's magic. I like that one. So yeah, so as we can see, these are all like cartoon. That it doesn't make sense because, okay, so supposedly this popped out of nowhere, and we're gonna go over that. That's called the quantum fluctuations. Let me see if we can get this. Let's go. We're gonna go to the quantum fluctuations. So we're gonna go over this now. So the quantum fluctuations in quantum physics, the quantum fluctuations is a temporary random change in the amount of energy point in space. Did you guys get that? In quantum physics, a quantum fluctuation is a temporary random change in the amount of energy in a point in space. You guys right? We could go over that over and over. It keeps saying that. It'll keep saying that. In a point of space. Okay? So let's go back to the cartoons. Okay? So in a point of space. So basically this is space right here. This right here. And let's click on it. Okay, so this is space, the inside. Okay, that's space. This is the edge of space. Can you see it? Over here. This is the edge over here too. See, that's the edge of space. And this space popped out from here. The quantum fluctuations. It says right there. Quantum fluctuations. Quantum fluctuations. Okay? That's how this popped out. There was a quantum fluctuations. Where did they come from? They don't know. They just made that up. And then space pops out. But as we can see, if space is moving and expanding, that means space must have this edge right here. It has to have an edge. This is not my model. This is your guy. This is the Globy model. This is the edge. There must be an edge. If it's expanding, like this cartoon is showing, there has to be an edge. The cartoon's showing us. And then when we go to see how it started, it says the quantum fluctuation began the inflation. That's what it shows. But then when we go back to read about the quantum fluctuations, okay, the quantum fluctuations says, again, temporary random change in the amount of energy in a point in space. Where did this quantum fluctuation come from? Let's go back to this. Let's go back to the expansion. Where did this quantum fluctuation started space? We see that. But yet again, we'll go back to it says that it's in a point in space. So where did this quantum fluctuation come from if no space existed yet? How is there an energy in a point in space when space doesn't exist yet? It doesn't exist yet. Space did not exist before the quantum fluctuation. And we could read this over and over. I suggest you guys start reading about this. This Globies. This is your guys' These aren't my words. These are your words that you guys are reciting. Matter of fact, you're not reciting these words. You're reciting other shit that you don't even got right. And we're going over right now the real words that you should be saying, which are even are just well, actually, they're just as stupid as the lies that you're saying right now because they're both all fairy tales. But as of right now, I mean, that's what it is. Quantum fluctuations, simple and clear. Okay, simple and clear explanation.